In today's video, let us understand fast Fourier transformations. The valuation of financial derivatives is a central problem in quantitative finance. While the Black-Scholes-Merton model provided a revolutionary closed-form solution for European options, its foundational assumptions have been shown to be inconsistent with observed market behavior. This section establishes a theoretical framework that moves beyond these limitations, positioning the Fourier transform not merely as a numerical technique, but as a fundamental paradigm for pricing derivatives under more realistic models of asset dynamics. The elegance of the BSM model stems from its simplifying assumptions, primarily that the underlying asset price follows a geometric Brownian motion. This implies that the asset returns are log normally distributed and that volatility is constant over the life of the option. However, empirical analysis of financial markets reveals significant deviations from this idealized world. Financial returns are known to exhibit fat tails, meaning that extreme price movements occur far more frequently than predicted by the normal distribution. Furthermore, the volatility of an asset is not constant. It is itself a stochastic process. This is evidenced by the positive autocorrelation of the squared returns, a proxy for volatility, which persists over several days, contradicting the constant volatility assumption. In the options market, these realities manifest as the volatility smile or skew, where options with the same maturity but different strike prices have different implied volatilities, a phenomena that cannot be explained by the BSM model. These empirical facts necessitate the development of the more sophisticated models capable of capturing these features. The financial literature has produced a rich family of such models, including models like the stochastic volatility models, such as the Heaston model, which treats the volatility as a mean reverting random process, allowing it to fluctuate over time and be correlated with the asset returns, thereby generating volatility skews. And also, we have jump diffusion models, like the Merton's model, which have sudden discontinuous jumps onto the continuous Brownian motion to account for the impact of significant unexpected news events on asset prices. Next, we have Levi processes. This broad class of models, such as the variance gamma process, describes asset dynamics using processes with stationary independent increments that can accommodate jumps, skewness, and kurtosis in a more general and flexible manner. Primary challenge with these advanced models is that they often lack a closed form expression for the probability density function of the terminal asset price. This makes direct calculation of the option price, which is discounted expectation integral involving the PDF, intractable. This is where the Fourier transform provides a powerful alternative path. The Fourier transform is a mathematical operation that decomposes a function into its constituent frequencies. For a function f of x, its Fourier transform at a frequency u is denoted by this symbol and is equal to the integral from minus infinity to plus infinity of f of x times e to the power of negative index iux with respect to x. Conversely, the original function can be recovered from its transform by the Fourier inversion formula. So, f of x is equal to 1 by 2 pi, an integral from minus infinity to plus infinity of the Fourier transformation of f or the frequency u times e to the power of minus iux into du. In the context of probability theory, the characteristic function CF, denoted by this, of a random variable x, is defined as the Fourier transform of its probability density function, px. It is the expected value of e to the power of iux and is given as characteristic function is equals to expectation on e to the power of iux, which is equal to integral of minus infinity to plus to infinity of e to the power of iux into the probability density function px into dx. Crucially, the characteristic function uniquely determines the probability distribution. It contains all the same information as the PDF. This duality is the key to Fourier-based pricing. The price of a European call option is the discounted risk rental expectation of its payoff, max of st minus k comma 0, letting s subscript t is equal to ln of st be the log price at maturity t, and k is equals to ln of k be the log strike. The price ck can be written as an integral involving the risk neutral PDF qt of s as ck is equals to e raised to minus rt times the integral from k to infinity into e to the power of s minus e to the power of k into qt into s ds. While the integral is difficult to solve if qt is unknown, we can leverage the Fourier immersion formula. By expressing the option price in terms of Fourier transforms, the problem shifts from integrating against an unknown PDF to integrating against a known characteristic function. The specific formulation that makes this numerically viable was developed by Carr and Madan. The utility of this entire framework hinges on a remarkable property of many advanced financial models. While the transition densities are often intractable, the characteristic functions are frequently known in closed analytical form. This is particularly true for the entire class of affine jump diffusion models, which includes the Heaston model, and for many Levi processes like the variance gamma model. This fact creates a powerful and efficient division of labor in quantitative finance. One stream of research focuses on deriving the characteristic function for new and increasingly realistic asset price models. Another stream, which we are discussing about today, focuses on developing and refining numerical methods to price any option given an arbitrary characteristic function. This approach represents a fundamental paradigm shift in financial modeling. Instead of being constrained to models where the PDF is known, practitioners can define a model directly by specifying its characteristic function. Furthermore, the Fourier transform provides a unifying mathematical framework. The pricing algorithm remains largely the same regardless of the underlying model complexity. Whether dealing with stochastic volatility jumps or stochastic time, the process is to substitute the appropriate characteristic function into the Fourier pricing integral. The model's complexity is neatly encapsulated within the formula for its characteristic function, making an FFT-based pricer a remarkably versatile and foolproof tool for a quantitative analyst. While the theoretical link between characteristic function and option prices is elegant, its direct numerical implementation faces significant hurdles. The seminal work of Carr and Madan provided the crucial engineering steps to transform this theoretical relationship into a practical, high-speed algorithm using the fast Fourier transformation. Now, let us dissect their approach and understand the core problem they identified and the ingenious solutions they devised. Standard numerical algorithms for computing Fourier transforms and the FFT in particular rely on the function being transformed belonging to the space L square, meaning it must be square integrable. A function f of x is square integrable if the integral of its squared modulus is finite, which means integral from minus infinity to plus infinity of mod of f of x squared dx should be less than infinity. Simply saying, an equation like this should be less than infinity and not infinity. The standard European call price CK, where k is equals to ln of k is the log strike, fails this condition. As the strike price k approaches zero, the option becomes deep in the money. Its value approaches the value of the underlying asset minus the discounted strike, which for small k is approximately the spot price, S0. Since Ck approaches a non-zero constant as k tends to minus infinity, its square is not integrable over the entire real line. This mathematical inconvenience prevents the direct and naive application of the FFT to the call pricing function. So, math. So, so this is the mathematical inconvenience we discussed about, blocking the usage of the FFT. The central innovation of the Carr-Madan method is to modify the call price function to make it square integrable. This introduces a damped call price, denoted by small c pk, and is equal to e to the power of alpha k into actual call price function ctk, where alpha is always a positive constant known as damping factor. The purpose of multiplying by the exponential term e to the power of alpha k is to force the function to decay to zero at the problematic limit. As k tends to minus infinity, the term e to the power of alpha k goes to zero exponentially, overpowering the constant behavior of CTK and ensuring constant behavior of the call price and ensuring that the modified function, the damped call price, is well behaved and square integrable. This mathematical pre-processing is the key that unlocks the use of FFT. With the square integrable function in hand, the next step is to find its Fourier transform, which is given by psi t of v is equal to integral from minus infinity to plus infinity e to the power of ivk into the call price of capital CTK into dk, which is equal to integral of minus infinity to plus infinity e to the power of ivk into e to the power of alpha k into the damped call price or small ctk into dk. Now, Har and Madan showed that this transform can be expressed analytically in terms of the characteristic function of the log asset price, ST. The derivation involves substituting the integral definition of CTK and changing the order of integration. This results in a remarkably clean and powerful formula. Psi t of v is equals to e to the power of minus rt into phi t of v minus alpha plus 1 into I whole by alpha square plus alpha minus v square plus I into 2 alpha plus 1 into v. Once psi t of v is computed, the modified call price can be recovered by a Fourier inversion. So the modified call price or CTK is equals to 1 by 2 pi into integral from minus infinity to plus infinity of e to the power of ivk times psi tv into dv. So from this modified call price, we can calculate the actual call price, and it is obtained by reversing the damping. So capital C Tk is equals to e to the power of minus alpha k into small ctk, which is further equal to, now after substituting the value of the small ctk which we just calculated into this equation, we will get the actual call price equal to e to the power of minus alpha k by 2 pi into integral from minus infinity to plus infinity of e to the power of ivk into psi t into dv. A naive Fourier representation of the option price has a similarity in its integrand at the origin, or u is equals to 0, which is an evaluation point for the FFT. The Carr-Madan formula, by requiring alpha greater than 0, ensures that the denominator of psi t of v is non-zero at v is equals to 0, thereby removing the singularity and making the integral suitable for numerical computation with the FFT. The brilliance of this method lies in its transformation of the problem. Instead of attempting to apply a numerical tool to a mathematically ill-posed financial object, Carr and Madan first re-engineered the financial object into a mathematically well-behaved one. This principle of mathematical pre-processing before numerical computation is a cornerstone of effective computational finance. The choice of the damping factor alpha is not arbitrary and represents a crucial trade-off. While a positive alpha ensures the damped call price decays for the negative log strike, the term e to the power of alpha k grows exponentially for positive log returns or log strikes, potentially jeopardizing integrability in that direction. For the modified call price to be square integrable, a sufficient condition is that the Fourier transform evaluated at the origin, or psi t of 0, is finite. Looking at the formula for psi t of v, this requires the numerator phi t of minus alpha plus 1 whole into I is finite. From the definition of the characteristic function, phi t of u is equals to the expectation. So this condition becomes phi t of minus of alpha plus 1 into I should be equal to the expectation, which should be further less than the infinity. This establishes a profound link between the numerical damping parameter alpha and the tail properties of the underlying financial model. The choice of alpha is constrained by the existence of 1 plus alpha-th moment of the terminal stock price. For models with very fat tails, the range of the permissible alpha values may be restricted. Different models impose different constraints. For Levi processes like the variance gamma or the CGMY models, explicit bounds on the alpha and can be derived from the model parameters. In practice, a common heuristic is to calculate the theoretical upper bound for alpha and choose a value that is function of this bound, such as 1/4 or 1/2 to ensure stability. While the Carr-Madan paper focused on the specific problem of pricing a European call option, the underlying principle has generalized into a powerful result known as the Carr-Madan spanning formula. This formula shows that any twice differentiable European payoff function g of st can be replicated by a static portfolio consisting of cash, the underlying asset, and a continuum of the out of the money puts and calls. And this is given as g of st is equals to g of f plus first derivative of g of f into st minus f plus integral from 0 to f of k minus st superscript plus into double derivative of g with respect to k into dk plus integral from f to infinity st minus k superscript plus. Here superscript plus means that we are checking for the max of the function or 0. So st minus k superscript plus into g double integral of k into dk, where f is constant and typically the forward price. This result demonstrates that the set of vanilla options forms a basis that can be used to construct any arbitrary payoff. This has a profound implications allowing for the model-free pricing and application of complex derivatives, and it forms the theoretical basis for instruments like the VIX index, which replicates a variance swap using a portfolio of options. The fast Fourier method for calls is thus a specific computationally efficient application of this much deeper and more general principle of spanning and replication. The versatility of the fast Fourier pricing method stems from its ability to accommodate any model for which the characteristic function is known. Now, let us understand the most important of these models. presenting their SDs, the financial intuition behind the parameters and their important characteristic functions and their unique Fourier signatures. Now, first let's look into the Heaston's stochastic volatility model. The Heaston model is a cornerstone of modern quantitative finance, providing a significant improvement over the BSM framework by allowing the volatility to be stochastic. The model is defined by a pair of coupled SDs under a risk-neutral measure. So the first SD for the stock price, ST, is equals to D of ST is equals to R ST dt plus root over of VT into ST DWT1. And the second SD is D of VT is equals to K into theta minus VT whole into dt plus sigma into root of Vt dWt2, where dWt1 into dWt2 is equals to rho dt. So as said, the first equation describes the asset price St, which behaves like a geometric Brownian motion but with a time-varying variance Vt. The second equation gives the dynamics of the variance itself. It is modeled as a CIR process, also known as a Feller square root process. This process has two key properties. The first property is mean reversion. The term k into theta minus vt pulls the variance vt back towards a long-term average level theta at a speed determined by k. This captures the empirical observation that periods of high or low volatility tend to be. The second property is non-negativity. Provided the Feller condition 2k theta is always greater than or equal to sigma square is met, the root vt term ensures that the variance process will not become negative. Let us understand the five parameters of the Heaston model. The first parameter, V0, is the initial variance, or the starting level of the variance at time t is equals to 0. It controls the overall vertical position of the smile, or the volatility square. The second parameter, kappa, represents the mean reversion speed, or the rate at which the variance Vt reverts to its long-term mean, theta. A high kappa means volatility spikes are short-lived. The next term, theta, representing the long-term variance or the long-run average level of the variance that the process is pulled towards, and it primarily controls the level of the smile for long-dated options. The next term, sigma, represents the volatility of volatility. It measures the volatility of the variance process itself. A high sigma implies a large and rapid fluctuations in the volatility. The last term, phi, or the correlation, is the correlation between the asset price's Brownian motion WT1 and the variance's Brownian motion WT2. The reason the Heaston model is so popular is that, despite its complexity, it admits a semi-analytical closed form solution for the characteristic function of the log price xt is equals to ln of st. This tractability arises because Heaston model belongs to the class of affine models. For such models, the logarithm of the characteristic function is known to be an affine function of the state variables, in this case just Vt, with coefficients that are solutions to a set of ordinary differential equations known as Riccati equations. The characteristic function phi t of u is equals to expectation for the Heaston model is given by phi t of u is equals to exponential function of c of t comma u plus d of t comma u into v naught plus iu into ln of s naught. Here, tau is equals to t at maturity, and the coefficients c of t comma u and d of t comma u are as follows. C of t comma u is equals to I into R into U into T plus K into theta by sigma square whole into K minus rho into sigma into I into U minus D whole into tau minus 2 into ln of 1 minus G into e to the power of minus d tau by 1 minus G, and d of tau comma u is equals to kappa minus rho into sigma into I into U minus D by sigma square whole into 1 minus e to the power of minus dt or minus d tau by 1 minus g into e to the power of minus d tau. And the intermediate variable d is equal to root of rho into sigma into I into u minus k square minus sigma square into minus I into u minus u square. This formula is the analytical engine that powers the FFT-based pricing for the Heaston model. It is important to recognize a subtle but crystal economic assumption embedded within this standard formula. The price of two sources of risk means the market is incomplete, and the risk neutral measure is not unique. A specific measure is chosen by specifying the market price of volatility risk, which dictates how investors are compared for bearing unhedgeable volatility risk. Houston's original paper made the convenient assumption that this price is directly proportional to the variance sigma of Vt is equal to sigma Vt. This specific assumption is what leads to the tractable PD and the well-known characteristic function above. Fast Fourier transformation methods applicability extends far beyond the Houston model. Its power lies in providing a unified pricing framework for any model with their own characteristic function. Now, let us look at the Merton's jump diffusion model. To capture sudden large price movements caused by major news events, Merton proposed adding a compound Poisson process to the standard geometric motion. The characteristic function of the log price in this model is simply the product of the CF for the diffusion part of the BSM and the CF for the jump part, which brings a consequence of their independence. So, phi of Merton of U, characteristic function of Merton of U, is equal to characteristic function of BSM of U into characteristic function of jump of U. Characteristic function of Merton of U equals exponential of I times R minus sigma squared over 2 minus lambda k times TU minus sigma squared times U squared times T over 2 multiplied by the exponential of lambda T times e to the power of I mu j into U minus delta j square into U square by 2 minus 1, where this is basically Black-Scholes diffusion part and this is basically the jump part. And lambda is equals to the jump intensity and the log jump sizes are normally distributed with mean mu j and variance delta square j. The variance jump model is a pure Levi process that offers a more flexible way to generate skewness and kurtosis than the simple jump diffusion models. It can be intuitively understood as a Brownian motion with drift, but where time itself flows randomly according to a gamma process. This subordination naturally leads to a flatter tail distributions. Despite its complex nature, the VG model has a remarkably simple and tractable characteristic function. The characteristic function of a VG model of U is equal to 1 minus I into mu into U into theta into V plus sigma square V by 2 into U square whole of this to the power of minus t by v, where sigma is the volatility of the Brownian motion, and v controls the variance of the time change, and theta controls the drift of the time change. Now let us understand the discrete algorithms which we'll be using in our implementation in Python. We will focus on the Houston model as a primary example. I will be providing commented code and explaining the critical choices involved in the setting up of the numerical algorithm. The Fourier inversion integral required to obtain option prices is a continuous integral over an infinite domain. To compute this numerically, we must perform two approximations. The first one is truncation, means that the infinite integration range is to be truncated to finite intervals. The second one is discretization. The integral over this finite interval is approximated by a sum such as the Riemann or Simpson's rule sum. This discretized sum is precisely the form of discrete Fourier transformation. A naive implementation of DFT for endpoints requires O(n) square arithmetic operations. The fast Fourier transformation is a collection of highly efficient algorithms like the Cooley-Turkey algorithm that computes the exact same DFT but with a dramatically reduced computational complexity of the order O of n log n. The accuracy and stability of the FFT pricing method depends critically on a proper setup of the computational grid. This is often a source of confusion for practitioners. The key parameters are interrelated through the properties of the DFT. There is a fundamental duality between the grid in the frequency domain and the grid in the log strike domain. The spacing in the frequency domain, which we denote by eta, and the spacing in the log strike domain, which we denote by zeta, are linked by the relation zeta into eta is equals to 2 pi by n, where n is the number of points in the grid. The relationship implies a trade-off. A finer grid of strikes requires a wider integration range in the frequency domain. Conversely, a finer sampling in the frequency domain, which is necessary to avoid aliasing errors for long maturity options, implies a wider spacing between the resulting strikes. A practitioner must understand this duality to design a grid that covers desired strike range with sufficient resolution without introducing numerical artifacts. Now let us understand the key grid parameters we'll be using. The first one is n. N describes the number of grid points. It determines the number of strikes priced and the resolution. It must be a power of 2 for optimal performance of the algorithms like the radix2 FFT algorithms. Typical values range from 2 to the power of 10 to 2 to the power of 14, but 2 to the power of 10 is commonly used. The eta represents the frequency spacing, controls the range of log strikes that will be priced. Alpha represents the damping factor, It ensures the integrability of the call price function must satisfy the moment condition expectation less than infinity. A value between 0.25 and 1.5 is common and is chosen to optimize accuracy for at the many options. We will now build a Houston pricer using Python. The implementation follows the Carr-Madan approach. First, we implement the analytical formula for the Houston characteristic function, which we derived earlier. This function will be the core engine of a price. We are defining a function called the Houston char func, where U represents the Fourier transform variable, T represents the time to maturity, R represents the risk-free rate, V naught is the initial variance of the asset, kappa is the mean reversion speed of the variance, theta is the long-run average variance, sigma is the volatility of the volatility, rho is the correlation between the asset prices and the volatility, and S naught is the initial stock price. Now, the first step is to compute D. So D is basically one of the roots that determines the shape of the volatility's distribution. We use the formulas which we discussed earlier to compute these factors like D and G and C. After computing small d, we compute G. Think of G as a correction factor that keeps track of how volatility feedbacks into itself. Now, after computing G, we compute C. This is the C term of the Houston characteristic function. The first part, R into U into 1J into T, accounts for the risk-free growth of money over time. The second part encodes how the variance mean reverts back to its original term level, theta. The logarithm term comes from solving the Riccati ODE. After computing for C, we compute capital D. This is the D term, which captures how the initial variance V0 propagates into the future. After this, we put this all together into the Houston characteristic function, which is equal to exp of I into U into ln of S0 plus capital C plus D into V0. The small d and small g are used to compute C and D. Next, we construct the main function that sets up the grid, evaluates the Carr-Madan integrand, and performs the FFT. To improve accuracy, we incorporate Simpson's rule weights into the sum before the FFT. The function setup here is Houston FFT pricer, which takes in the initial stock price, the strike prices we want option values for, the maturity, the risk-free rate, the kappa, V naught, theta, sigma, rho, which are the Houston model parameters, the alpha, which is the damping factor, and the number of FFT grid points, and eta. First, we define the grids. We calculate zeta, which is the corresponding spacing in the log strike domain, and V is just the grid of the Fourier frequencies. So here we're building two worlds. One is the Fourier world, which is a U by V grid, and a strike price world, which is a K grid. Now, we want option prices for range of strikes. The K grid is the set of log strikes corresponding to the FFT output. The K min centers the strike grid around the current spot price. Next, we initialize Simpson's rule weights. Because when we turn the Fourier integral into a discrete sum, we want accuracy. Simpson's rule is a higher order quadrature method. It replaces a plain Riemann sum with a weighted one. Next, we calculate the characteristic function. Here is the magic. Option pricing boils down to the plugging of the Houston characteristic function into Fourier space. The shift alpha plus 1 j damps the payoff function to ensure integrability. In these steps, we build the Fourier integrand. The first fraction is the Carr-Madan Fourier kernel. The np dot exp minus r of t discounts to the present value. The denominator alpha plus iv into alpha plus I plus iv comes from transforming the call payoff into the Fourier space. The exponential function np dot exp of I minus v came in aligns the strikes with the FFT grid. Finally, Simpson's weights and eta gives us a discretized integral. Instead of summing over thousands of terms, we let FFT to do the job in O of n log n time. This gives us a vector of call prices corresponding to the K grid. Next, we divide by pi to normalize, by multiply by exponential function of minus alpha k to undo the earlier damping factor. Now Ck are the actual call prices across the strike grid. Now we convert from the log strike back to the strike price and interpolate smoothly between the FFT grid points. And we finally evaluate the interpolated call prices curve at the actual strike prices, we wanted. These are the parameters set up, and this is where we call the function. And this is a plot showing how the call prices of the Houston model are. So if we can see, for a lower strike price than the spot, the call price is higher. Whereas for a higher strike price, the call price kept on gradually decreasing. This completely aligns with the characteristic of equity index options, confirming that the negative correlation parameter phi is correctly generating the leverage effect. Having established the theory and implementation of this FFT method, now let us understand a critical analysis of its performance and discuss its potential numerical pitfalls and position it within the broader ecosystem of the quantitative pricing techniques. The accuracy of the FFT method is subject to two primary sources of numerical error, both stemming from the approximation of a continuous integral with the discrete sum. The first one is a truncation error. This error arises from replacing the infinite limits of the Fourier integral with a finite range. The magnitude of this error is determined by the tails of the integrate that are cut off. It can be controlled by choosing a sufficiently large integration range and an appropriate damping factor. The next error is the discretization error. This error results from sampling a continuous function into discrete points. If the sampling frequency, which is controlled by eta, is too low, high frequency components of the function can be misinterpreted as low frequency components, a phenomenon known as aliasing. This error is managed by ensuring that theta is small enough to capture the most oscillatory parts of the integrand. There is an inherent trade-off in managing these errors. A smaller theta reduces aliasing, but for a fixed n, also reduces the integration range, potentially increasing the truncation error. Achieving high accuracy requires a careful balancing of these parameters, often guided by empirical testing and convergence analysis. The power of this approach rests on a series of interconnected principles. First, the characteristic function provides a complete description of a stochastic process's distribution, offering a tractable alternative when the probability density function is unknown. This has enabled a shift towards designing models directly in the frequency domain to capture observed market phenomena. Second, the Karl-Madan method provided the critical mathematical engineering to make Fourier pricing numerically visible, transforming a non-square integrable call price function into a well-behaved object amenable to the FFT. Third, the method's elegance lies in its versatility, providing a unified pricing algorithm for a vast section of models, from Heston stochastic volatility to various jump diffusion and Levi processes, with the model's complexity neatly encapsulated within its characteristic function. Finally, the unparalleled computational speed of the FFT, comprising an entire smile of options simultaneously, has established it as the indispensable tool for the critical task of model calibration, anchoring theoretical models to market reality. The relevance of the Fourier methods is not waning. Research continues to extend their reach into new and more complex domains. Techniques are being actively developed to apply FFT-based pricing to multi-asset options, such as spread and basket options, by working with joint characteristic functions. Furthermore, Fourier analysis is proving essential for tackling cutting-edge rough volatility models, which challenge classical stochastic calculus but appear to better capture the observed behavior of market volatility. The enduring ability of Fourier analysis to translate complex stochastic problems into more tractable analytical forms ensures its continued and central role in the ongoing evolution of the quantitative finance.